All right, Dr. Tor, let's get into some specifics. You sent me a photo of some textbooks that are showing that the primordial soup is still being taught. And, one of the things that I find very interesting about this, and I'd like to get your opinion on, is if you think this is something that we need to address and needs to, be for the next generation to really have a solid foundation of what's realistic. Do we need to talk about this? Should we just concede and say, hey, yep, primordial soup, that's the way life evolved? Or it actually needs to be addressed on a more fundamental level?
Yeah, it needs to be exposed for being a bunch of nonsense, because so many people have bought into this, as I showed on the video. And it's being taught not just in high schools, it's being taught at the college level, introductory. So here's high school level. This is a whole list that was sent to me by Casey Luskin, and he only went through 2018 because that's what he had access to. But these are high school, and then there's high school AP biology, and here's intro college and upper level college. So there's 41 textbooks that he had access to that are teaching the primordial soup model. So this idea that it's not taught beyond the 6th grade is wrong. It's being taught even in the universities, where there's some lightning strikes on a puddle or a pond, and some cells some molecules came together, formed a cell, and those cells then formed higher organisms. This is so untrue. This needs to be not just that they need to stop teaching it, they need to backtrack and to say everything we've said about this is wrong because we have no idea that this is how it happened. So yeah, this is just clearly wrong, and it's right up into the upper level college textbooks, biochemistry textbooks.
So it's not nearly as much of an outlier as it's proclaimed to be. And we're not. Well, we have questions now, so it's actually not there anymore. You're saying,
no.
yes, it is, and yes, it is still being taught as fact.
Everything in the Farina video was wrong, and here's another one. I mean, everything that the man said was wrong, and this is right up into the universities that this is being taught, and that's why so many people are confused on this subject, as you saw in the survey that I had shown.
Yeah, it really is. It's kind of disturbing, in my opinion, when you think about like how many people's approach to different levels of discovery and understanding have been malaligned due to this. I like to use the term "fruit of a poison tree." And so kind of how I feel about a lot of these things. Now, there's obviously there's a plethora of different paradoxes, if you will, in origin of life research. If we, let's say we solve the homochirality problem, which is probably the one that's with what we know now, probably even less likely, but let's say we do. Does that completely, create a new dynamic? Like, hey, if we solve this one problem, that means we've solved life. Or is it just hey, we figured out a process by which something we know is possible can be replicated. We don't necessarily know how it formed in a prebiotic environment.
No, that would not solve everything. To say we solved the homochirality problem it doesn't state this for what it is. There's so many different structures you're going to have to solve the homochirality problem for. You have to solve it not for one amino acids, but you have to solve it for a bunch of amino acids, not all 20, but you have to solve it for 19 of them. And for a couple of them, they have 2 stereogenic centers. So you got to solve. So solving it for one of them doesn't solve it. You have to solve it for all of them. Then, if you solve it for the amino acids, then you have to solve it for the sugars. But it's not just one sugar. It's many sugars that you have to solve it for, and those have multiples of stereogenic centers. So it's a much harder problem. And so you have to solve it for the sugars before you can solve it for DNA or RNA. And so it stops it right there. And then the lipids also are homochiral. You got to solve it for that. And solving it for that is different than solving it on these other ones. So to say that we could solve the homochirality problem, for what class are you talking about? And for which molecule? To solve it for one molecule doesn't solve it for all the other molecules, even within the same class. So you solve it for one sugar, you still have all the other sugars you got to solve for. Solve it for one amino acid, you have 18 other amino acids you got to solve it for. And so it doesn't address, it doesn't solve it. Now, let's say you could solve it for all of the different classes. Now what? Well, now you have to also solve the synthesis of them, not just the homochirality problem, without using this relay synthesis game, then you have to solve the polymerization. How do you get these things to hook together? Remember, amino acids don't hook together. How do you get sugars to hook together so that you can control the regio and stereochemistry? Remember, I told you millions of different combinations in just a hexamer, just 6 of them. And that's using just a homopolymer of just one particular sugar. And then how are you going to solve the DNA polymerization problem for the nucleotide polymerization problem to DNA, or the harder one, the polymerization problem to RNA? RNA is just super hard because it depolymerizes by itself, just chemical depolymerization where the 2' attacks on over and clips it. And how do you keep the 2', 5' polymer from forming? I mean, all of these are just huge problems. And then even if I gave them that, then it's the order. You need the proper sequence. So that's why I said you give them that too. And then it's the assembly problem, and then everybody will be stuck there. So no, you solve one problem, it solves like almost nothing within the problem set. Almost nothing within the problem set is solved by solving one homochirality problem.
Right, and it seems that in line with what you're saying there, you have additional quasi-paradoxes, if you will use the word, of, hey, turns out we might actually need to have these solved simultaneously. And which is a whole new problem, right? Well, not a new problem, but a whole another layer of like, wait a minute, what are we talking about here? That's kind of the way I approach it when I read through these things, and I'm like, so per your admission, you ultimately would at some point you have to have all of these things simultaneously in existence.
Exactly.
But if I can solve this one, then that accounts for the other ones. I'm like, yeah, but you have to have the same, and you talked about this in one of the videos, like you have to have all of these things not only in existence at the same time, they have to be in existence in the same place. And not just, they're down the street. We have to be from correct me if I'm wrong on this, but from an actual chemical binding perspective, they have to literally be next to each other.
In the same puddle. They all have to be in the same puddle. They all have to be in the same pond. And they have to be there at the same time. Because if you're going to talk about geological time frames, I mean, to have a molecule, any molecule there, it's going to decompose by the time you're waiting for the other one. They all have to be there at the same time. And then when you want to do the cell assembly, you got to have them all nearby. And then it's the concentration problem. I didn't even get into the concentration problem. Just you have these things. You would have to have so much of this material if it were to be in the ocean. And even if you want it in your tidal pool, you dump it in the tidal pool where when it fills up again, they pour back out. I mean, it's a hard concentration problem. And the way some of these people are solving it, they say, well, they're putting things together in pastes recently. I mean, this is such a joke. You have it such high concentration that it's in a paste. It's in a paste. I mean, this is crazy high concentration. And how do you deal with it like that? Where did you get nucleotides in such a high concentration that they don't even dissolve anymore? I mean, all of these are hard problems.
Dr. Tour, this, what I'm about to tell you, will probably quasi make you fall out of your chair at the stupidity of it. I was recently told that homeostasis had no significance in whether or not a reaction was feasible in a prebiotic environment. Of like, it doesn't matter if the pH could be completely different. The temperature, all that doesn't really have any bearing on whether or not it's a naturally occurring reaction. And I was stunned that I'm like, hang on, isn't it recognized that part of the reason a lot of these reactions are able to happen is because of the balance that's being artificially, quote unquote, artificially maintained inside of the cell? Am I wrong on that?
Yeah, well, people speak of homeostasis mainly in a living system, and they have to have this balance of reactions going on. But when you're talking about even individual reactions, you got to have the right pH, you got to have the right temperature. You have so many things have to be well aligned in this. So many things have to be well aligned to do this, and you can't just randomly put up pHs and put down pHs. It doesn't matter. No, everything matters on chemical reactions. You just shut them down very quickly. Purity is a big thing. All these origin of life chemists, they're generating lots of different compounds, and they say, here it is, and then these can polymerize. Tell me, when you did that condensation polymerization, did you purify it? Was it pure? Or did you just do it on a whole bunch of others? Because you can't do a condensation polymerization without having pure materials. And that every biomolecule that's a polymer is a condensation polymerization. It's a step growth polymerization kinetics, and you have to have high purity. I'm not talking 90% purity. I'm talking 99.99% purity to get anything of any reasonable molecular weight out. And everybody tries to overlook this problem.
Interesting. One of the things I've found very interesting in our conversation so far today, Dr. Tour, is there's been multiple instances where you're like, oh yeah, there's this problem too. You haven't said it directly like that, but I've seen it in your in your language and your reaction. You're like, wait a minute, that's a whole nother thing I didn't cover in my series that is a problem for this discussion. Now, one of the things that I was very struck by, excuse me, in Farina's video was where he tried to imply that you had no understanding about like information in general and just DNA, and he went so far as to say that you were just like completely ignorant in the fact that DNA contains information, which I was rather struck by given the fact that you've had talks about this. But I wanted to kind of put things into context, and I really thought he took the clip he used for this. I think he took it out of context, and I wanted to kind of showcase to folks. And you can react if you want to. Otherwise, I just really wanted to show people this, and I'm going to cover a few other points on this. Let's just let the video play for itself.
It's also incredibly anti-intellectual. We can't make planets and stars either. Does that mean nature can't have made them spontaneously?
There would be no inherent information in the DNA. But even if we gave them the DNA in the structure that they wanted, they wouldn't know how to put all the components together.
This is just nonsense. He is saying there is no information inherent in the DNA when DNA is inherently information because of the way genes code for proteins when expressed. Jim is way out of his element when it comes to informatics. Then he says something unintelligible about how if the DNA was provided, we still wouldn't know how to put the bacterium together. Again, this is ridiculous, because the DNA is literally what contains the instructions to put the bacterium together. I find it hard to believe that Jim does not understand how gene expression works, so this may just be dishonesty on his part.
Well, there's so many facets to that I find I'd love to cover, but we'd have to do a whole nother video on that. Now, ladies and gentlemen, I'm going to play the full clip. Well, there's much more to this interview, but the clip that he drew from the main interview over on Discovery Institute that Dr. Tour did.
We do not know how to build even a simple bacterium. The simplest bacterium with its 256 protein coding genes, we have no idea how to build it. First of all, we don't know how to build the molecules, the 4 classes of molecules that are needed for it. We don't know how to, even if we had those 4 classes of molecules, assemble them even into the simplest of bacteriums. We don't know how to do that. One can do that with the technologies we have today. We can make technologies, but we can't even make the simplest bacterium. Anybody who would say something contrary does not know what they are talking about. Show me the demonstration. Nobody has ever done it. And it's not because of lack of effort. It's not because of lack of will. First of all, they haven't been able to get the molecules to do this. And if they could make the molecules, even if we were to give them the molecules, they wouldn't have the information. There would be no inherent information in the DNA. But even if we gave them the DNA in the structure that they wanted, they wouldn't know how to put all the components together because of the sophistication within a cell. The interactomes, meaning that the interacting connectivity between the molecules, the van der Waals interactions, all of these have to be in the right place and in the right order for a cell to function. We don't even know how to define life, let alone knowing how to spark it to begin.
So I think that puts a slightly different interpretation on what you were saying there, the point that was being made, and the overall context versus what Dave Farina tried to extrapolate from that. I find it interesting that he actually did recognize that there's information in DNA, given there's so many folks who try to claim there's not especially here on YouTube. Now, Doctor, did you like to respond to any of that, or you feel free not to? I know this is kind of a hot button issue that's been being approached.
I mean, I addressed this in my video. I mean, okay, I'll give you the DNA. Just giving DNA does not give you a bacterium. He says DNA, this DNA codes for that. Okay, you have the DNA. Then how do you have the bacterium? This is the challenge that I put before people. I'll give you not just the DNA, I'll give you the RNA, I'll give you the peptides and the nucleic acids, the lipids. I'll give you everything. Now construct the bacterium. If you think you can just mix that all together and the bacterium starts forming, no. But he says it's dishonesty on my part. And then he says the DNA would have no information in it. And he says that's how proteins code for this. No, we're talking about the inherent DNA. What gave the DNA this order? So you have three bases are going to define for you what amino acid is going to be there, but you have no starts, you have no stops. Every word is going to be a random mishmash of letters. It doesn't have the inherent information. Now, if he wants to talk about something called Shannon information, Shannon information is getting information from randomness that was used in signal theory in the 1940s by this researcher Shannon. But that does not give us this what's called specified information, which is not my term. That was a term that was actually, I think, coined by Leslie Orgel, a origin of life researcher himself. And that doesn't give you the specified information that you have for a higher organism. But if Dave wants to argue at the end of the day, look, I'm not an informatician, I have no business here. Okay, fine, I'll concede, I'll back off. Let Dave, the informatician, tell us all about this. But there's plenty of other people on the internet that know lots about informatics that are going to address this. And they knew exactly what I was talking about. The inherent information needed to encode, to build proteins that are going to be the nanomachines that are going to build the systems around, that is very hard to fathom. So this is what I was talking about. This randomness, this information that proceeds out of randomness, the Shannon information, is irrelevant here, in my opinion. But again, I'm not an informatician.
Well, I completely agree with you. And it's this topic is one of my personal passions in trying to help people understand, a lot of the points that you're making there. And the irony is that Shannon himself, like the Shannon information and the principles of information theory, just the raw information was only step one. Then when you're getting into communication theory, now you've got the functional and the specified information and the coding and all those different things and the value assignments. And this is where semantics starts to come into play and pragmatics. And there's a few things actually in terms of our conversation I wanted to showcase to folks. I really think, and it really amazes me how many people, even PhDs that I've interacted with, are unaware of this reality. So I want to share a few things. So this goes back, things I'm going to talk about go back quite a ways. But this is from, so Hubert Yockey was a major leader in information theory, and he did quite a few things in Origin of Life, a plethora of different things. But this is one of his books, Information Theory, Evolution, and the Origin of Life, kind of case in point, on the topic, right? Cambridge University Press, 2005. Information, transcription, translation, code, redundancy, synonymous, messenger, editing, and proofreading are all appropriate terms in biology. They take their meaning from information theory, Shannon, he's referencing Shannon 1948's paper, and are not synonyms, metaphors, or analogies, which is ironic because that's something we hear very often, especially in the YouTube universe. People claim, oh, it's not real information. You're just claiming it's like kind of sort of like information. It's not actually, and then it's definitely not specified information, which is which I find very interesting. And so kind of going to the next stage, somebody that you talked about, Orgel, but let's talk about Jack Szostak. It's a paper he did, and it's functional information in the emergence of biocomplexity. So Nobel Prize winning Origin of Life researcher. He's on the topic along with these other authors, but he also recognizes the point that's being made and its significance in Origin of Life. Then in context of, the overall, well, more in detail on this, but this applies back to the point you were making, one of the points you made earlier, Dr. Tour, about a lot of folks in biology specifically not recognizing the significance of what role this plays. And it's actually a pretty interesting paper. If you have take time to read it, actually get into great detail about how it needs to be focused on. But one of the things I found very interesting in this paper was we believe that no real progress will result from the recognition of the prominent role of information in life phenomena unless information theory is integrated into biology as physics and chemistry have been. I don't know how much more significant of a statement you can make if you're putting the role of specified information on the same playing field as physics and chemistry. I mean, that's a pretty, would you agree with that, Dr. Torrey? That's a pretty direct statement.
Yeah. It certainly ups the challenge here in Origin of Life. And these biologists would see that there's a lot of information we have to deal with. I think it'd be great to bring that into the education.
Absolutely. Here's another example as from what's code biology. This is a fantastic paper, by the way, but one of the things I really wanted to cover is today, in other words, we have the experimental evidence that the genetic code is a real code, a code that is compatible with the laws of physics and chemistry, but is not dictated by them. Our problem, therefore, is to take stock of this reality and to account for it. So to me, when you really think about that, and by the way, the paragraph above this, they're referencing the experimentation, the different experiments and the studies that have been done to reach this conclusion and to separate away from just, chemical, we can account for it with chemical affinity and different things of that nature. And it's like, no, here's where we're at now. We have to account for this. We can't just ignore it and claim that it happened and we'll figure out something from a chemistry perspective. But what he's saying is we've already gone down that rabbit hole and this is where we're at now. And this went back to this more in-depth paper from Hubert Yockey. Again, title, Origin of Life on Earth and Shannon's Theory of Communication. So again, communication, not just information theory. But there's one piece that's, by the way, this whole page, anybody who wants to claim that I'm cherry picking, go read the entire paper. You'll find even more detailed defense of what I'm about to say. But it is a curious fact, highly relevant to the origin of life, that the genetic code is constructed to confront and solve the problems of communication and recording by the same principles found both in the genetic information system and in modern computer and communication codes. The origin of a rather accurate genetic code is a pons asinorum that must be crossed to pass over the abyss that separates crystallography, high polymer chemistry, and physics from biology. As I mentioned above, there is nothing in the physiochemical world that remotely resembles reactions being determined by a sequence and codes between sequences. The evidence of a genome and the genetic code divides living organisms from non-living matter. And like I said, that's that paper goes into even greater detail of things that substantiate the point that's being made there. But and I have plenty of other papers on this, expand upon this concept even further. And what I find so interesting is in the origin of life research, things you're talking about in relation from the chemistry perspective are in my opinion, every bit as significant as what these gentlemen I was quoting were referring to. And it's like, we have to have both of these. Like, you have to account for both of them. And if you can't account for the basics of the chemistry, how do you possibly account for semantic information that's a literal, follows the exact same principles of computer code?
Yeah, and the information doesn't come from the chemistry. The information is actually primary. The matter upon which we're storing it is secondary. The information is actually the primary thing. Information can be stored on all sorts of mediums. It happens to be stored in a biological system in DNA. But and then I talked about how information can also be stored in RNA and then in proteins, and then in carbohydrates, but the inherent information is the primary thing. With chemistry, the synthetic chemistry I'm talking about is just the medium upon which it is stored. So this is just amazing. There's a whole relation here. If I could just divert for 2 seconds, give me just a diversion for 2 seconds. It says in John chapter 1, verse 1, in the beginning was the Word, and the Word was with God, and the Word was God. It's the Word in the beginning. And then in John chapter 1, verse 14, it says, and the Word became flesh and dwelt among us. And we beheld his glory as of the only begotten from the Father. There's this whole idea of information. It started with information in verse 1 of John. And then the Word took on a medium, and it came in Jesus Christ. And so the Word is actually primary here. And you got to have this code. I mean, this code is critical. And how these people want to just slough off the code, I mean, it's just really something here. Oh,
And Dr. Tur, with your, I know you've dove into, storing information, having different memory devices on the molecular level.
yeah, I have a
The
whole company that builds memory. We build
right,
electronic memory in
right.
silicon chips. That's what
Well,
they
yeah,
do. It's a public company.
well, and what I find so interesting about this whole topic is, and I'm sure you're probably very aware, there's massive amounts of investment going into using DNA for data storage. And I
I
mean,
have a
huge.
company that does that too.
Do you? Awesome. I knew it. I knew it. So you're very aware of this. So, I mean,
Oh yeah, I'm very aware. I mean, it's not fast. It's good for long-term archival storage.
right.
But yeah, I mean, I got a whole company on it. But what do I know about information? I'm way out of my league. What do I know?
Well, what I find very interesting is I've actually brought this up to we're working on DNA computers and everything else, and I was watching a video from Microsoft. They were out presenting their latest machine for doing printing, data printing and such, and data access. And I'm sitting there like, I just had a conversation with a supposedly educated individual who told me there is no data being stored in DNA, while simultaneously there are billions of dollars being invested by the biggest tech companies in the world to figure out the most efficient way to store and access and retrieve data inside from the DNA medium, while simultaneously I have people telling me that, oh, it's just chemicals. There can be no information in chemicals. And I'm like, it's the point you made. It's the medium. The medium has no bearing on what the information actually is.
Mm-hmm. Yeah.
And it's very striking.
Medium on which there's a whole DARPA program on storing information on DNA. There's the whole DARPA program going on right now. That one of my companies is participating in that. It's for accessing. It's a way of accessing the information on the DNA. That's what one of my companies is doing, along with some other things. But yeah, that's right.
That's amazing. Some of the papers I've read on the different methodologies trying to be employed for the access and the writing and creating error correction code logic and everything else for the access. I'm sitting there reading through this stuff and just being like, wow, that's awesome. And then what I find so ironic is there's another paper I didn't show, but they're talking about the natural error correction mechanisms in a natural, biological system being vastly superior to the best things that we've been able to come up with so far.
Yeah.
And it just cracks me. I honestly, I get a good chuckle out of it. I'm just like, you're telling me that there is no information here, or it's not specified, it's not actually functional, it's random, while simultaneously we are recognizing and being able to quantify error correction codes, which are vastly superior to the best ones we've been able to come up with.
Right. Go to Roswell Biotechnologies, and you'll see the company, and you'll see on chip, you reading DNA on chip. So you have DNA interfacing with silicon chips, and then how you deal with error correction. I mean, it's all there. It's all there, and the information medium is the DNA.
Well, hopefully, ladies and gentlemen who are watching this, we have firmly established that Dr. Tur does understand this. He actually has ownership in a company that does this. So perhaps we can kind of dismiss Dave Farina's assertion that Dr. Tur doesn't have enough understanding to have an opinion on how this relates to origin of life research. Now, okay, last question before we get into the comments. So let's talk about input. Let's put this back in context of origin of life. We kind of touched on this earlier, but the second a person walks into a lab, they are inputting information into the method and the process, at least in my opinion. Can we talk a little bit about, the steps, the notebooks, and, maybe put this in context of like your nano cars, right? I know you talked about this before and how it related to the human input variable in its relation to origin of life.
Right. So as soon as the chemist walks in that laboratory, there's been human input. As soon as the chemist has ordered the chemicals that are in that laboratory, there's input. When you want to have origin of life, you have to have no human input. No human input. And you say, okay, well, we need a little bit to get the thing set up. Okay. But there's massive human input on origin of life experiments. I mean, to the extreme, you have to be an extremely good chemist to carry out these reactions. You look at at some of these origin of life laboratories, it's just, for example, my friend Lee Cronin, and I consider him a friend. There's videos of his laboratory. I mean, with bunches of different flasks and tubes going between them and computers controlling the input into these tubes. It's like, this is massive human input. Where are you going to find that on an early Earth? Early Earth didn't have a brain. It didn't have input into this. And you have to say, well, this puddle spilled into this puddle. Okay, once. But then this puddle, and then this puddle, and then this puddle, and then this, and then this part fractionated out. And, you know, it's like in Dave Farina's video. And then a simple natural filtration. I'm like, okay, tell me about that filtration. How did that filtration occur? I mean, so many things people do. If you're going to really have origin of life experience, you can't touch any of these things. You can't do any of these things. And so if you're in this, Clemens Reichert got into this in his 2018 Nature's Communication article. He said, you got to devoid this of human input, and or else it's not really a biologically an origin of life, an abiogenetically relevant synthesis. Yet all of the syntheses that are out there are full of this. They're just full of human input, and so it's a huge problem.
Yeah, it's you know, the way you're outlining this and framing it, it almost seems like if humans with the input aren't being able to even get close and are actually realizing they're further and further away while they're obviously having input, then the probability and the plausibility of solving it, or it being let's say plausible, without the intelligent agent, to me seems to be getting more and more outlandish. I think it's kind of your point on like, hey, we need to do a moratorium and actually assess this. Is that kind of a fair point?
Yeah,
like this is why I'm saying we need to have a pause on this.
Right. No, I agree. We need to have a pause on this because it's just going crazy. I mean, even I was looking at some of Lee Cronin's YouTube videos from 7 or 8 years ago that are on YouTube, and he says, you know, in 7 or 8 years, we'll have really, you know, done this. You know, it's like trying to predict the return of the Lord Jesus, or trying to predict the rapture. You know, as soon as you put a prediction on it, you're going to be wrong. And he put this prediction on it, and he's so far away from being able to do this. God bless the man. I mean, but you know, when you say in 7 or 8 years you're going to crack this problem, it's a hard problem. Yeah.
All right, well, ladies and gentlemen, this is going to kind of wrap up our first portion of the interview. Now we're going to dive into the fun and frivolity of the comments. You will not want to miss this, so stay with us as we get into the funny, the focused on Dave, the challenges, the responses from colleagues, some great points, and then some of the haterade from the most adamant critics. So stay with us.